We're going to do some L'Hopital's rule examples that all result in the indeterminate forms 1 to the infinity, 0 to the 0, and infinity to the 0. Looking at our first example, we have the limit as n approaches infinity of n to the 2 over n.
So we'll have infinity in the base, and in the exponent, 2 over infinity is 0, so the indeterminate form is infinity to the 0.
Now, what we're going to want to do in all of these examples is we're going to want to use the fact that e to the natural log x is equal to x. We know that e and natural log are inverses, and so that's why this holds. So what we're going to want to do to start this problem is introduce that idea. So we're going to rewrite this as the limit as n approaches infinity of e to the natural log of n to the 2 over n. I've cleverly rewritten the expression in an equivalent way, but now I have natural log of n to the 2 over n. So with the introduction of logarithms, I get to use log properties. So I get to take this 2 over n that's in the exponent and bring it to the front of the log. So I have the limit as n approaches infinity of e to the 2 over n times natural log n. All right, so now we have a property of limits that says I can go ahead and pull this limit into the exponential because we have the correct continuity happening. So we can write this as e to the limit as n approaches infinity of this here, which I'm going to rewrite as 2 natural log n over n. So now I can focus on evaluating this limit here that's up in the exponent of the base of e. If we know our laws of dominance, this limit at infinity is going to end up being 0. N is growing bigger faster than natural log n. So this whole limit does equal 0. But for the sake of actually employing L'Hopital's rule, we're going to go ahead and solve this by taking the derivative of the top and of the bottom separately. So right now we have the indeterminate form infinity over infinity. So what we'll do is we'll go ahead and bring this up here. This is equal to e, the limit as n approaches infinity, of 2 times 1 over n. The derivative of natural log n is 1 over n, and the derivative of n, the bottom, is just 1. So what I have here is e to the limit as n approaches infinity of just 2 over n. And now we can really see, using dominance, I have a constant over n, which is getting bigger, so this, again, is going to 0. So we have e to the 0, which is equal to 1. In this example, I have the limit as x approaches 0 from the right of the quantity 1 plus x to the power of 1 over x. If I think about x approaching 0 from the right, the inside here, if this x is 0, is just going to be a base of 1. And then 1 over x, well, as x approaches 0 from the right, if the bottom is getting to be really, really small numbers divided into 1, this is going to infinity. So the case that I have is 1 to the infinity, which is an indeterminate form. And we are once again going to use the idea that I can rewrite the expression as e to the natural log of 1 plus x to the 1 over x. And then I can go ahead and bring the 1 over x to the front of the log because of log properties. So I have the limit as x approaches 0 from the right of e to the 1 over x times natural log of 1 plus x. And so now I'm going to have e in the base, and I'm going to bring the limit into the exponent. So I have the limit as x approaches 0 from the right of natural log of 1 plus x over x. So I have this quotient, and let's think about evaluating this limit now. So if I substitute in 0, I'm going to get natural log of 1, which is 0, and then over 0. So I have the indeterminate form 0 over 0, so I can apply L'Hopital's rule to this limit that's in the exponent. So I'm going to go ahead and bring my work up here and say that this is now e to the limit as x approaches 0 from the right of, well, here, the derivative of natural log of 1 plus x, that's going to end up being 1 over 1 plus x. So I'm doing the chain rule. times the derivative of the inside, which is 1, and then over 1. So the derivative of x on the bottom is just 1. And so now, if I think about substituting in 0 into x, I'm not going to have any issue anymore. So I'm just going to have 1 over 1. So the exponent, this whole thing, ends up just being 1. So my answer is e to the 1, which is just e. For this example, I have the limit as x approaches 0 from the right of x to the sine x. If we try direct substitution, we'll have 0 in the base, and sine of 0 is 0, so 0 in the exponent. We do have this indeterminate form. So let's go ahead and get started. We'll write the limit as x approaches 0 from the right of e to the natural log x to the sine x. And then we'll use our log properties and bring the sine x to the front of the log. So limit as x approaches 0 from the right, e to the sine x times natural log x. Now we'll go ahead and bring the limit into the exponential. So we have e to the limit as x approaches 0 from the right, but instead of writing sine x times natural log x, I'm thinking about using L'Hopital's rule, so I want a quotient, and that's a product. So I'm going to rewrite sine x using its reciprocal identity. Sine x is 1 over cosecant x. So I'm going to rewrite this product as a quotient, the quotient natural log x over cosecant x. All right, so now let's make sure this is an indeterminate form. So as x approaches 0 from the right, natural log x is going to be going down to negative infinity. And if I think about the cosecant x graph as I approach 0 from the right, that's going to go towards positive infinity. So I do have infinity over infinity case, so this is indeterminate. I can move forward with L'Hopital's rule. Now that we have some more space here, I'm going to write this as e to the limit as x approaches 0 from the right. Now, the derivative of natural log x is 1 over x. The derivative of cosecant x is negative cosecant x cotangent x. Okay, so let's go ahead and attempt to simplify this a little bit here. So we can go ahead and rewrite, let's think about this for a second. Cosecant x is 1 over sine x. So this piece right here is 1 over sine x. And then cotangent x is cosine x over sine x. And so we can go ahead and rewrite these. Let's see, this next line will be e to the limit as x approaches 0 from the right of, let's see, I have 1 over x over negative cosine x over sine squared x. So I'm multiplying 1 times cosine and sine times sine on the bottom, and then I can multiply by the reciprocal. Now, if you can do this work in your head, please feel free to. I'm just trying to show my work here. So this is 1 over x times negative sine squared x over cosine x. And so what we have, e to the limit as x approaches 0 from the right of negative sine squared x over x times cosine x. So if I substitute in 0, sine of 0 is 0, and then 0 times cosine of 0 is 0. We get indeterminate again, the indeterminate form 0 over 0 here. So what does that mean? We do L'Hopital's rule again. So making some more space, we have e to the limit as x approaches 0 from the right. Let's take the derivative of that numerator. That's going to be a chain rule. So we'll leave that negative there. We'll have 2 sine x times cosine x. So we're remembering that sine squared x is sine x quantity squared. So we bring that 2, leave the inside the same, times the derivative of the inside over, down here, what do we have to do? The product rule. So we have the first function is x, and we'll leave that guy alone. The derivative of cosine is negative sine x, plus, now we'll leave cosine x alone, times the derivative of x is just 1. All right, So now let's see if we have made any progress. If we substitute in 0, do we get an indeterminate form again? So if we substitute in 0, sine of 0 is 0. So this whole numerator is 0. But the big question is the denominator 0? And the answer is no. So we would have e to the 0 over 1, because this part right here, x times negative sine x, if I plug in 0, 0 times sine is 0, but cosine of 0, which is added, is 1. So the denominator is 1, and so 1 over, so 0 over 1 is 0, and e to the 0 is 1. Whew, that was a lot of work. We did the introduction of e to the natural log. We did L'Hopital's rule twice, and it required us to do both a chain rule and a product rule. Before wrapping up, I want to go over a couple of important limits that are worth knowing for future classes. For any real numbers a and b, if we have the limit as n approaches infinity of n to the a over n, that's always going to equal 1. And if we go back to the first example, we had the limit as n approaches infinity of n to the 2 over n, and we did all of that formal work involving taking e to the natural log of this quantity, and we got out 1 as an answer. So it turns out the answer is always going to be 1, regardless of that value of a, as long as it's a real number. And there's another limit worth knowing, the limit as n approaches infinity of the quantity 1 plus a over n, all raised to the power b times n. So for any numbers a and b, the answer to this limit is going to be e to the ab. And the way that we could show that is by doing that same process we've been doing for all of these examples, but it's just worth knowing because this does come up every so often in future classes. So recognizing this form will just save us that time.